Okay, here's some problems from section 9.1, some homework problems. It's number 15. And again, these are kind of a continuation of 11 through 20, where the directions are: tell whether the series converges or diverges. If it converges, give it some, pardon me. And if we look at this one, even though you look at the cosine, you want to see what kind of values it generates, so you need to write out some values. So this is the cosine of n times theta as n goes from 0 to infinity. So I wrote out some terms. When n is 0, the cosine of 0 is 1. When n is 1, the cosine of pi is negative 1. When n is 2, the cosine of 2 pi is 1, like 0. And then again, when it's 3 pi, it's negative 1, etc. So it's going to be oscillating. So the reason why we can check this is a sub n. The limit as n approaches infinity of a sub n. It does not exist because it oscillates between negative 1 and 1, so there's no limit. And remember, if the limit is not equal to 0, then it diverges. That means it does not, because if it converged, the limit would be equal to 0. If it does not equal to 0, then it does not converge. So therefore it diverges. Okay? That's that statement we talked about. Should be a theorem. Okay, let's take a look at number 16. So these are my terms: 3, negative 0.3, 0.03, etc. And they actually gave you the nth term, but I kind of wrote these out to kind of take a look at it. But it looks like the nth term is this. It looks like what we have is a geometric series where a sub 1, or the beginning first term, is 3, and the ratio is negative 0.1. And I just wrote it out like this so you can see this is 3 times negative 0.1. And 3 times negative 0.1 squared, that's another negative 0.1, etc., which follows this pattern. So it looks like my common ratio. I just keep multiplying by a tenth. And another way to take a look at this, if I take this 3, if I multiply, I take a tenth of that, I move the decimal 1 to the left, then 2 to the left, 3 to the left, 4 to the left. So this is what I have. So I have a geometric series. I have a common ratio of negative 0.1 and an initial term of 3. So since the absolute value of negative 0.1 is less than 1, it does converge. All right, and we can find the sum. They ask you to find the sum if it does converge. So I think they did have geometric sequences in mind. So this is my formula. Remember, the sum is equal to a over 1 minus r. A is 3, and r was negative 0.1, so it's 1 minus negative 0.1. which ends up being 1 plus 0.1, which is 1.1, so that's 3 over 1.1. And we don't really like decimals and fractions, so we can get rid of that decimal by multiplying the top and the bottom by 10. So I've got 30 over 11, and that's the sum. Okay, number 17. And I'm sorry I didn't have time to rewrite these, but a little bit late, but my notes are usually neat enough, so you shouldn't have trouble reading these. This is number 17, so we've got the sine of pi over 4 to the n, pi over 4 plus n pi to the nth. Well, when you see the sine, you're going to think, well, it oscillates, so it should definitely diverge because a sine is an oscillating function. But this is part of a generator that generates terms. So you have to write out some terms to see what's going on. So remember, it goes from n equals 0 to infinity, so I put some n's in to see what it looks like. And this is n equals 0. I should have put these down here. N equals 0, n equals 1, n equals 2. So you can see some n's and see what kind of series we generate. So when n is 0, it doesn't matter what's in here. Anything to the 0 power is 1, so that's no problem. Now when n is 1, if I put 1 in here, I've got the sine of pi over 4 plus pi. N times pi is 5. So that's going to be the sine of 5 pi over 4. And the sine of 5 pi over 4, remember that's going to be the square root of 2 over 2, but since it's 5 pi, it's in the second quadrant, so it's going to be negative. So it's going to be negative the square root of 2 over 2 to the first power. All right. Now, when n is 2, I've got pi over 4 plus 2 pi, which gets us all the way around, so it's back to the sine of pi over 4, which is the square root of 2 over 2, and that's going to be to an even power, so that's going to be positive. Well, that's going to be 2, so it's going to be squared. But This is also a positive, square root of 2 over 2, and since I'm going to be squaring these, then it's going to stay positive. So my signs will remain the same. So when I go to the third, this will be a negative. This will make this a negative. This will put this in a negative quadrant, and the cube will actually maintain the integrity of the negative sign. So I'm going to have these signs that will, in essence, alternate. Now, if I think of a sub 1 as my first term, if I multiply this by the square root of 2 over 2, I've got the negative square root of 2 over 2. Then if I multiply this, or if I put this term down, it's like multiplying this by another negative square root of 2 over 2 to get positive the square root of 2 over 2 squared. So it looks to me like I have a geometric series. My a sub 1 is 1, and my ratio is negative the square root of 2 over 2. And again, if you multiply this by this, you'll get this. If you multiply this by this, you get that. Okay, the square root of 2 over 2, well, the square root of 2 is about 1.414 over 2, or if you work that on your calculator, you're going to get a number that's less than 1. So since my ratio is less than 1, it converges. Okay, so my series converges because the absolute value of r is less than 1. It's negative, but I'm just worried about the absolute value. So now let me find the sum. So I'll put this in my sum formula. And I probably need to write that down so you see that over here again. The sum equals a over 1 minus r. Very important formula. So a is 1. So over 1 minus, and then my r is going to be negative. That's why I get the alternating signs. So 1 minus negative the square root of 2 over 2, which is the same thing as 1 plus the square root of 2 over 2. And then I can add these, and I just did the arithmetic. And let's see, I have 1 over 2 square root of 2 over 2 because I made a common denominator. And then I just inverted and multiplied, so that just became 2 over 2 plus the square root of 2, so I multiply the top and the bottom by the conjugate. Okay, so I got 2 times 2 square root of 2 minus 2 over, and then that's like a plus b times a minus b, so that's 2 squared is 4, minus square root of 2 squared is 2, 4 minus 2 is 2, those 2's cancel, so there was my sum. So that was 17. And let's see if we can get 18 on here. I think I can. It's not too bad. So if you can see that, you can always pause these and check it out. And here's number 18. I do this tonight. And this is my series, 1/2, 2/3, 3/4, 4/5, and they actually give you the nth term, a sub n term, n over n plus 1. Okay, well, if we look at this real quick, I mean, we know our limits. We know that the limit of this, as n approaches infinity, it's like a horizontal asymptote. The highest degree is 1. These are the same, so my limit is just going to be 1 over 1, which is 1. It's just the coefficients here. Or I can think of this as just being n over n because the 1 is insignificant. Still 1. I can think of it as being infinity over infinity plus 1, which is infinity over infinity. There's lots of ways I could do it, 3 or 4 different ways I could do it. I can use L'Hopital's rule because if I put infinity, I get infinity over infinity. If I take the derivative, I get 1 over 1, which is 1. Either way, there's 4 different ways to do it right there. In either way, it's 1. The limit is 1. The limit's not equal to 0, so remember, if the limit's not equal to 0, then it can't converge. So it must diverge. Remember, if it converges, the limit will be equal to 0. All right? If the limit's equal to 0, we don't know for sure if it converges, but if it does converge, the limit must be equal to 0. All right? If the limit's not equal to 0, then it can't converge. Therefore, it must diverge. Okay? So those help.